Hey guys, welcome back to the Fun-Filled Day of Science. It's Chapter 1, Section 3. It's Mr. Lewis here with you. This section is called Scientific Models. Obviously, right here is your bell ringer. Go ahead and read your bell ringer. Pause me. Read your bell ringer and go ahead and post it up there on Edmodo. Let's go ahead and get started. Dun, dun, dun. Our objectives today are going to be to describe how models are used to represent the natural world. We're going to identify three types, count them, three types of scientific models, and we're going to describe what theories and laws are. That is the objectives for today. Here we go. We're going to start off with our first type of model. Well, first off, what is a model? Is it me? Can I vogue? Yes, I can vogue. No, a model is not me, even though I am a French model. A model is not me. A model is a representation of an object or a system. That is what a model is. It can also be known as a prototype. So you have a model, you have prototype. It's the same thing. They're creating a representation of some type of system. Now, there are three major types of models, okay? When we talk about them, there are physical, mathematical, and conceptual. When we look at physical models, what we're looking at is things like this flower over here. They look like what they represent, all right? So this flower over here, this picture of this flower, which is from your book, the picture from over here, the flower, is a physical model because it looks like what it represents. Another example of a physical model would be, bada boom. Hello, I'm over here. All right, this right here would be another example of a physical model because it looks like what it represents, the globe. It looks like the Earth. That is one example of a physical model. It looks like what it represents. Now, is this globe over here that I just showed you, or this picture over here, is this a real picture? Can it really make its own food through photosynthesis? Do people really live right here? No, but that would be very cool. Where are you at? That'd be very cool if people lived right here, but people don't live actually here, and the blue is not really water, but it represents that, and that's what physical models do, okay? The next type of model is called a mathematical model. Now, mathematical models just are exactly what it sounds like. They use mathematical equations and data to come up with their model. Now, the example for that would be right here. Oh, look, this is our little weatherman right here. Oh, weatherwoman, sorry. And she was showing us that, oh, down here it's going to be beautiful. Look, Tennessee, we got sun. Yay, we have sun. Mathematical models use mathematical equation and data to come up with their model. All right. Now, as we all know, that these people here are usually wrong. They don't usually give us the right answer for as far as weather is concerned. And why is that? Well, if you look right over here, this is the reason. A change in a variable that was not thought of could cause the model to fail. So one tiny variable that they didn't take into account when they were designing what the weather was going to be for the day. That one little tiny thing could throw the whole thing off, and instead of having 80 degrees in sunshine, we have 70 degrees and downpours. So that's the reason why weathermen typically are wrong or can be wrong, is because of the fact that one unforeseen variable changed the entire model. All right, and you guys know that if you plug in a wrong number in an equation in Ms. Boyd's room, you're not going to get the right answer. And that's the same thing because you changed one variable. That one variable changes the whole answer. And same thing with these mathematical models. The last thing that we have, the last type of model is called a conceptual model. Now, conceptual models are just like what it sounds like. A concept is an idea. So they use familiar things to make comparisons to things that you can't see. Down here, they're talking about the Big Bang Theory, all right? And they say that's how the universe, evolutionists, that's how they say the universe began. They said that our universe, our world began, there was a massive star that exploded, and it created us. Okay, so that's what they have done. Now, the interesting thing is when they actually do the calculations for the Big Bang Theory, it says that the Big Bang Theory says that that's how everything was created. There are stars that are older than when the first star began, so their model doesn't really hold up. But that's beside the point. Another example of a conceptual model will be this right here. Dun, dun, dun. Now, you guys have seen this in my room, this is a model of an atom. Is this a real atom? No, but this is a model of what an atom looks like. This is a Niels Bohr model of an atom. Inside here, you have your protons and your neutrons. Outside here, these little nice little purple things, you have your electrons. This is a concept of a model of an atom, conceptual model, so that you get an idea what it could look like. Now, does it really look like this? No, but this is one way. This is the way that we have it set up, so it's easy for us to understand, easy for us to recognize when we see those models. All right, now. Models can be big, they can be small. Typically, we use models to represent things that are too big for us to see, that we represent things that are too small for us to see. So, example, el globo, this is the globe. The Earth is too big for us to really see it, but looking at a globe, we can see the placements of the continents on there. We can see the oceans and stuff like that. So looking at a globe, we can shrink down the size of the Earth down to something that we could hold in our hand, because he's got the whole world in his hands. Oh, I'm sorry. So the globe would be a model, and what they've done is they've taken something so large that we can't see the entire thing of, to make it small enough so we can see the globe. It's the same thing with the atom. Mr. Atom here. This is Mr. Aluminium, if you're British. Aluminum, if you're American. This is a model of aluminum, and obviously we can't see an atom of aluminum, so we have to create a model so we can get an idea of what it would look like. All right, so these models are useful for studying cells. We use these models to study objects like the Earth. We use models to study things that are too complex for us to understand. We use models for all those different things, so we're able to get an idea of how something operates or how something works. Now, models help us to build scientific knowledge. All right, that is an important key here, that they do help us build scientific knowledge, because it helps us explain and illustrate scientific theories. We're able to understand when we look at things, oh, okay, so we see how that works. Here's an example. First off, a theory is a unifying explanation for a broad range of hypotheses and observations that have been supported by testing. Theories and models can change as new observations are made. Notice, a theory can be changed, okay? Just like the Big Bang theory can be changed. So ideas that are theories, they have been proven over many hypotheses, tested over many hypotheses and many observations, but they are not a law. Okay, it just tells us this is typically what's going to happen. And as new information becomes available, we can change those different things. Now, here's an example of what we're talking about. In your book, you see a picture of the plum pudding model right here. Now, this was the atomic model. This is Thomson's atomic model. This was the atomic model in 1897. And basically what they said is the atom was a big ball of goo with a few bits of hard pieces sticking out. Now, these bits of hard pieces sticking out are electrons. Now, they didn't know that at the time, but that's basically what they symbolize. This is what Thomson thought the atom looked like. And for a long time, that's what we thought the atom looked like. However, scientists in recent years have decided we have better microscopes and those kinds of things, extremely powerful microscopes that can go ahead and look at these atoms to see what they look like. Now, these atoms now we know have a center that has the protons and neutrons in the nucleus, and we also know that the electrons float around in a cloud. That the electrons are it's just a cloud. It's not as neat and organized as this is, where the electrons are in these nice, neat circles and orbits, which is what they thought when I was in school. But you know, since the time I've been in school, and I was in your grade, in 8th grade, they've changed that model. And so now the model has changed to where we have an electron cloud. That's where the electrons are. You cannot predict where they are. But to make it easy for us to conceptually understand and to realize, we still use the Niels Bohr model of the atomic atom. All right. Now, scientific laws are different. Scientific laws are are the results of many different experimental observations. Now, they tell you what happens, not why it happens. So a law will tell us what happens, like the law of gravity tells us that if we drop something, you know, if I were to take something and drop on the desk, it's going to fall and hit the desk. It tells us that it's going to happen, but not why it happens. Let's make sure you understand that. So after the theory correctly predicts something many times, it becomes a law. Now, oh my goodness, it is Review time, it's time for the review. Scientists use models to represent an object or a system. Three major types of models. There's a physical, mathematical, and conceptual models. Physical models look like what they represent. Mathematical models use mathematical equations and data. Conceptual models are systems of ideas that make comparisons with familiar things to illustrate ideas. Models are used to represent things too big or too small to see. They help illustrate theories, explanation for some phenomenon based on observations, experimentations, and reasoning. The scientific laws is a summary of many experimental results and tells us how things work. And law of conservation of mass. Ooh, we didn't talk about that one. That's something that you need to know for the rest of the year. You need to understand. The law of conservation of mass says that during a chemical change, this is a law, during a chemical change, the total mass of the materials formed is the same as the total mass of starting materials. In other words, law of conservation of mass says nothing can be created or destroyed in a chemical change. Okay, you cannot create atoms and you cannot destroy atoms in a chemical change. They just change forms. All right, other than that, I don't think there's anything else for us to talk about. Hope you guys enjoyed that video, and I'll be seeing you in the future.